Hi, welcome back. In this example, we're going to learn how to determine the explicit formula for a sequence in function notation. So it's still going to be an explicit formula, but it's going to have a function notation form. All right, so it says here for each term in the sequence, make a table of values, then use the term number and term and calculate the finite differences, and then graph the sequence using the ordered pairs, and then determine an explicit formula for the nth term using function notation. Let's start by making the table of values. So we'll write n for the term number. Okay, and then we'll write t of n for the table. So t of n, this is actually the term, right? So this is the term number, and then this column is the value of the term. So my first term is a 7. We're going to write 7. Second term is 12. Third term is 17. Fourth term is 22. So you notice it's a lot like x and y, right? This could be like our x values. That could be like our y values. Okay, it says create the finite differences. So 12 minus 7 is 5. Okay, 17 minus 12, sorry, also 5. 22 minus 17, also 5. So those are my first differences. We can see it's going up by a constant 5. Okay. It says then graph the sequence using the ordered pair. So if I were to do a graph here, so we'll do 1, 2, 3, 4. And we go all the way up to 22. So I think I'll mark off 25 up there. And then we'll do 20, 15, 10, and then 5. So that's a good scale for that. So 1, 7, that would be about right here. 2, 12, that would be about right here. 3, 17, that would be about here. And 4, 22, be about there. Sorry, a bit higher actually. Okay, so there's my graph. Now determine an explicit formula. So sometimes doing this finite difference is good because it helps us get some insight into the sequence. So if there's a constant difference of 5, that means this is going to be a linear relationship, which we can see from the graph. And we know that the slope is 5 because it's always going to go up by 5 to the next term each time. So it must have something, it must look something like this. Now it says to use function notation. So when I write out my explicit formula, instead of writing t of n, I'm going to write it as f of n because it's going to be a function. Okay, and I know there's a slope of 5, so it has to look something like 5n, a linear relationship. Okay. Now, the thing is, I know I need something in here to make this work. So, like for instance, if I put 1 in, if I take that 1 and plug it in for n, I get 10. And 10 is not 7. So I can tell that it's off a bit. So usually what I do here is I just write in a value b, and then we can solve for it. Okay. So again, real quick, this 5 is just my slope, okay, which you can usually find in the first difference column. It's the constant number. And then this here is going to be the y-intercept. So to find that, I can just substitute at any point I know. So we'll say sub in 1 comma 7. So I'd have 7 equals 5 times 1 plus b. 7 equals 5 plus b, therefore b equals 2. Okay, so that means my final function is going to be 5n plus 2. Okay, I could also check this with another point as well too, like 212, and see that I also get b equal to 2. Another thing you could do is you could look at this table and you could try to find the y-intercept. We know the y-intercept happens when the y-axis, it's when the x is 0, right? And we're along the y-axis. So um, this term up here, 1, 7, we'd almost have to go back 1 in order to get the y-intercept. So if you follow the pattern, these are always going up by 5 each time. Well, if you wanted to predict the one back 1, we know we'd have to go down by 5, so it'd have to be a 2. So we'd have 0, 2, if you kind of follow the pattern. So that would be a y-intercept right there. Okay, so anyway, that's how we could find the explicit formula in function notation. So function notation is real easy. So the function notation, instead of writing it as t of n, we switch it to an f. Okay, let's try the next one. Okay, I'm just gonna create a little bit more space here. So let's start by doing the table of values. So we'll have n for the term, and then t of n for the term value. So term number, and then the actual term itself. So first term is 1, second term is 10, third term is 25, fourth term is 46. Okay, next thing you got to do is the finite differences. 10 minus 1 is 9, 25 minus 10 is 15, 46 minus 25 is 21. Okay, that's my first difference. Okay, those are not constant. So I don't see a linear relationship here. So let's go ahead and do the second set. So 15 minus 9 is 6. 21 minus 15, also 6. So our second differences are constant. So that means we're not going to have this linear form anymore. If the constant occurs in the second column, if you remember previously, it means it's going to be quadratic. Okay, it's going to have a quadratic or degree 2 form. So there's a little bit of a trick to try to come up with our equation. So our explicit formula, well, let's graph first. We'll do that first. And we'll be able to see how we have that quadratic form. So we got 1, 2, 3, 4. We got to go all the way up to 46. So I'll make that 50, 40, 30, 20, 10. So we have 1, 1, that would be about here. Then we have 2, 10. Then we have 3, 25. Then we have 4, 46. So I was tempted to draw a line through here, but you can see this has a nice curve. So it has a quadratic form. So my function, my explicit formula and function notation is going to follow this form. It has to be quadratic. So notice I kind of made it look like ax squared plus bx plus c. That would be like our standard form for quadratic. So when you do the finite differences, there's something special about the number that's in here. So this number that's constant, it's always twice the value of this number in front A. So what I mean by that is A is always equal to half of the constant number. So for us, it's going to be 6. So half of that is 3. Okay, this is a rule. I'm not going to spend too much time explaining why. You can just kind of accept it. But um, this leading coefficient A is always going to be half the value of this in the second column. That's as long as it's a quadratic, right? As long as the constant is in the second column, it's always going to be half that value. So what this means is we have, so far for our function, we have A is 3, so we're going to have 3n squared plus bn plus c. We just need to find the other coefficients here, b and c. So to do that, we have a lot of information that's given, so we can use it. We'll substitute in some points. So we'll substitute in 1, 1. So we're going to have 1 equals 3 times 1 squared plus b times 1 plus c. So we have 1 equals 3 plus b plus c. So this gives us an equation. I'm going to call it 1. So what we'll do here is we're just going to clean this up a little bit. Subtract 3 from both sides. Cancel that out. So we'll have negative 2 equals b plus c. I'm going to call this equation A. So now what we're going to do is we're going to substitute in the next point. The next point we had was 210. We're going to plug that into this equation. So 10 is going to go in for f, and then 2 is going to go in for the ends. 10 equals 3 times 2 squared plus b times 2 plus c. So 10 equals 3 times 4 is 12 plus 2b plus c. Subtract 12 on both sides, and I'll get negative 2 equals 2b plus c. I'm going to call this equation B. You probably know where I'm kind of going with this. So we now have two equations with two unknowns, B and C. So we can either do substitution or elimination to try to find the values of B and C. So I'm going to go ahead and I'm going to do substitution. Okay. So I'm just going to create a little more space here. Okay, and I'm just going to highlight those two equations that we have. So we'll say in A, isolate for C. So we have negative 2 equals B plus C. I want to get C by itself, so we'll subtract B from both sides. That'll leave us with this. Now what I'm going to do is I'm going to sub C equal to negative 2 minus B into equation B. So what I mean by that is I'm going to take this and I'm going to plug that directly up there for C, because this is what's equal to C. So just take this, substitute that in. The nice thing is everything will now be in terms of B, and we can solve for B. So here's my substitution. Okay, so we have negative 2 equals 2b minus 2 minus b. Negative 2 equals 2b minus b is just b. Okay, therefore B equals 0. So we can now say sub B equals 0 into this equation up here. I plug in 0 for B, I then now know C. So into equation A. Okay, there's the bracket showing the substitution. Okay, so I found out all my parameters. We found out A, doing the finite differences and taking half the value. And then doing substitution, we found out B and then C. So I'm just going to write the final equation up here. Therefore, the function is going to be 3n squared. And remember, B is 0, so we're going to have plus 0 times n. And then my constant term was negative 2. So really, this whole thing is not really there. It's just 3n squared minus 2. Now, there's probably other ways you could have determined this equation. So this approach that I just took here is a little bit systematic. It works all the time. So you do your finite differences and first find A, and then use substitution to get the rest, B and C. The other way we could have did this is we could have backed up one term, and we could have found when n was 0 that we could have followed the finite difference pattern. So knowing that there's always a difference of 6 between these, this number needed to be 3. And so there's a difference between these two of 3. So this would have needed to be negative 2. So I know that the point 0, negative 2 exists. And if you substitute 0, negative 2, 0 in for n, you can see that it works. We would have got negative 2. So that's just another way that that could have been done. A lot in this chapter, like we're going to be trying to come up with equations that fit. Most of the time, we don't need to do a really large process like we've done here. For the other ones, it's going to be a little bit more intuitive. You're going to look for the pattern and you're going to try to come up with the equation. So both work really well. And as you practice, you'll get really good at them too. Okay, we just have one more example left, so I'll see you in the next video for that.